Okay, in the next two videos, we're going to work example problems from the definite integral section of the textbook. So all of these problems are related to the definite integral. However, we have not gotten to the fundamental theorem of calculus at this point. That's not until the next section. And so without the fundamental theorem of calculus, we have no idea how to calculate a definite integral using anti-differentiation. In the future, that's how you calculate a definite integral. You can do it quickly and easily. At this point, all we know is the definition of the definite integral as an infinite sum, as well as we did learn some properties of the definite integral that we can use, as well as we did learn some properties of the definite integral that we can use to solve definite integrals. And so for all of these problems in this video and the next video, that's the lens that we're looking at the definite integral through. Okay, first problem, evaluate the Riemann sum for f of x is equal to x minus 1 along this interval with 5 subintervals, taking the sample points to be the right endpoints. Explain with the aid of a diagram what the Riemann sum represents. So what is the Riemann sum? Well, okay, here's the definition of the definite integral. This is the symbolic notation, but here's the actual mechanics of the definite integral. The Riemann sum is this portion. So you have the Riemann sum, and when you take the limit as n goes to infinity of the Riemann sum, then it becomes the definite integral. But before you take that limit as n goes to infinity, you just have the Riemann sum. And so based on this definition, this xi star, whether you're using left endpoints, right endpoints, midpoints, whatever, any of those setups is a Riemann sum. Okay? And so it's saying here, evaluate the Riemann sum for this function along this interval with 5 subintervals using right endpoints. Okay? And so we don't have to draw the function, but let's go ahead and draw the function. All right, so the y-intercept is at minus 1. And the slope is 1. So 1, 1. All right, so we could draw a line going through those 2 points. Well, let's make sure 1, 2, 3, 4, 5, because we want to go all the way to minus 6. And 1, 2, 3, 4. Okay. So there we go. And we're going from minus 6, 1, 2, 3, 4, 5, 6, minus 6 to 4. Okay, so we're looking for the net area. It's going to be this, the area of this triangle minus the area of this triangle. So we expect this integral to be negative. But we're not taking the integral. We're just doing a Riemann sum, but still, a Riemann sum is it's an approximation of the integral, so we still expect the Riemann sum to be negative. Okay, and so what we're going to do is, with the right endpoints, the notation for Riemann sums is you've got the upper interval is b, and in this case that's going to be 4. The lower interval, the lower limit of integration is minus 6. That's a. Delta x is b minus a divided by n, and in this case n is equal to 5. So b minus 6 divided by 5 is equal to 4 plus 6, which is so 10 divided by 5. So delta x is 2. Okay, and then x0 is a. x1 is a plus delta x, which is 2, so minus 4. x2 is a plus 2 times delta x. Okay, so then x3 we can see is going to be 0. x4 is going to be 2, and then x5 is going to be b. xn is going to be b, is 4. Okay, and then these are the right endpoints. That's what's nice about the right endpoint Riemann sum. It's easier, the easiest to work with as far as the math goes, because these are the right endpoints. x1, the first rectangle, this is the right endpoint. The second rectangle, this is the right endpoint. So the R5 is, we do the sum from I is equal to 1 to 5, f of xi delta x. Okay, so what is this? Well, first of all, we can factor out the delta x, so we could take out a 2, and now we just need to sum the f of xi's. So what is the f of, we start with 1, f of x1, what does that mean? It's f of minus 4. What is f of minus 4? Minus 4 minus 1, that's minus 5. Okay, what is f of x2? F of minus 2. That's minus 2 minus 1, that's minus 3. Okay, what is f of x3? F of 0 is minus 1. What is f of x4? That's f of 2. That's 1. F of x5, 4 minus 1, that's 3. So what we've got is minus 5 minus 3 is minus 8, minus 1 is minus 9, plus 1 is minus 8, plus 3 is minus 5. So R5 is equal to minus 10. Okay, now what does this mean? We come to each point, and so if we come here and we draw our intervals, it's every 2. Delta x is 2. We're going to get 5 total. One, two, three, 4, 5. Okay, now with the right endpoints, we make rectangles. So here's the right endpoint. Okay, here's the right endpoint. That's the height of the rectangle, is the right endpoint. And now we go up here. The height of the rectangle is, here is negative, right? Negative 5, negative 3, negative 1, positive 1. Well, this goes to, should be here. Positive 3. 1, 2, 3. This isn't drawn to scale, but it should be at positive 3. And so we're calculating this, the area of all these rectangles, and we're saying that that's the area under the curve. Okay, that's not the best approximation, but if you take the limit as n goes to infinity of Rn, then it would hug the curve almost exactly, and that's defined to be the area. Okay, the graph of a function f is given. Estimate the definite integral from 0 to 10 of f of x dx using 5 subintervals with right endpoints, left endpoints, and midpoints. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 0 to 10. So with all 3 of these cases, the delta x is going to be 2. Why 2? Because we're doing 5 subintervals. So if you break this from 0 to 10 up into 5 subintervals, the delta x is going to be 2. Okay, so I'll draw out the delta x's here. Okay, now if we're using right endpoints, what does that mean? R5. What does that mean? That means the height of the rectangle is going to be the function evaluated at the right endpoint x value. That's what that means. Okay, and so, but what we're doing though to estimate this with 5 subintervals, we're estimating the area, the net area under this curve with 5 rectangles. And we're going to sum the areas of those 5 rectangles to estimate this. Each rectangle for all 3 of these cases is going to have delta x is equal to 2. It's going to have a width of 2. The height of the rectangle is going to be, that's what's going to change. The height of the rectangle in part A is going to be the function evaluated at the right endpoint of the interval. In part B, it's going to be the function evaluated at the left endpoint. In part C, the midpoint. So R5, I mean, we can write, let's do it like this. Okay. This is going to be left 5, and then this is going to be mid 5. Okay. So in all 3 cases, we can factor out the delta x. So now all we're going to be doing is inside of here, we're going to be summing the heights of the rectangles. All right, the first rectangle at the right endpoint, what is the function evaluated at the right endpoint? It's -1. Okay, what for part B, what's the function evaluated at the left endpoint? It's 1, 2, 3. It's +3. You see? See how that's how it can be different? You see how you can get negative rectangle areas and positive rectangle areas? And you see how it would be to really get this definite integral correct, you'd want to increase the number of subintervals way past 5. You don't want to, if you're trying to do a good estimation, you don't want, when you switch between the right endpoint and the left endpoint or the midpoint, to have this drastic of a difference. Going from a height of a rectangle is -1 to 3 for the same, when you're talking about the same rectangle, as far as the same, like the first rectangle or the second interval, you don't want to have this drastic of a difference. So this is, you really want to have more subintervals to do a good estimation, but they're just trying to illustrate the concept. What about M? Okay, the function evaluated at the midpoint is 0 for the first interval. Okay. The second interval, here to here, what's the function evaluated at the right endpoint? It's 0. Left endpoint, -1. Midpoint, -1 as well. Okay. Third interval here, right endpoint, -2. Left endpoint, 0. Midpoint, -1. Okay. Fourth interval, right endpoint, 2. Left endpoint, -2. Midpoint, 0. Okay. Final interval, right endpoint, 1, 2, 3, 4. Left endpoint, 2. Midpoint, 1, 2, 3. Okay, that's it. So -1 minus 2 is -3, plus 2 is -1, plus 4 is 3. 3 minus 1 is 2, minus 2 is 0, plus 2 is 2. -1 is -2, plus 3 is 1. That's it. But remember, if you set up these as a Riemann sum, so as a function of n, just in general for n, and you took the limit as n goes to infinity for R, the Rn, Ln, Mn, they all converge to the exact same area, which is the net area under this curve. Use the midpoint rule with the given value of n to approximate the integral. Round the answer to 4 decimal places. Okay, so what they're saying here is that, remember, for a definite integral, it's the limit as n goes to infinity of the Riemann sum. But what they're saying here is they're saying ignore the limit as n goes to infinity and just do the Riemann sum with n is equal to 5 using the midpoint. And what you want to note about that, just remember that the Riemann sum, so you're not having the limit that n go to infinity, a Riemann sum is an approximation for the integral. And that makes sense. Like if you do a Riemann sum with n is equal to 100, that's an approximation for the integral. And that's what like numerical methods is about. If you have integrals that you can't evaluate analytically or it's just too hard or whatever, you can do approximate integrals. And so, but if you're doing an approximate integral, then it depends if you use the midpoint or the right endpoint or the left endpoint or some other point, you're going to get different answers for the integral. They should be close, but they're going to be, unless you're taking the limit as n goes to infinity, they're going to be different. And if you're taking the limit as n goes to infinity, then people often just use the right endpoint rule to set it up, because that's mathematically the easiest, because the way the endpoints are defined. However, if you're doing an approximation and you're choosing between like the right endpoint, the left endpoint, or the midpoint, it's advised to use the midpoint if you're going to choose between those three. Because with the midpoint, you kind of both overestimate and underestimate, so it cancels out. All right, so we're going to do the Riemann sum here using the midpoint rule with n is equal to 5. So how do we do that? M5 is what? Well, we can factor out the delta x. What's the delta x going to be? The delta x is b minus a, so 2 minus 0, divided by n. So 2/5, okay? So we can factor out the 2/5. Why? Because we're summing the areas of all of the rectangles that are being used in the approximation. But the width of every single rectangle is exactly the same. It's going to be 2/5. So you can factor out that 2/5. And now we're just summing the heights of the rectangles. Okay, so what's the height of each rectangle going to be? Well, we know that. So x sub 0 is a. X sub 1, but this is like the notation for general Riemann sums. X sub 1 is a plus 1 times delta x, so 2/5. X sub 2 is a plus 2 times delta x, so that would be 4/5. X sub 3 is a plus 3 times delta x, so that's 6/5. X sub 4 would be a plus 4 times delta x, 8/5. And then x sub 5 is going to be b, which is 2. So a plus 5 times 2/5 is 2. Okay? But these are the right endpoints. These are the right endpoints. That's why the math is easier. If you're going to do a Riemann sum as n goes to infinity, they say, well, just use the right endpoints, because you could just plug these directly into the function. But we're using the midpoints, so we don't say, like, we're still doing the sum. The Riemann sum for mn, okay, is the sum from I is equal to 1 to n of f of x whatever delta x. We still look at it like, okay, when I is equal to 1, we're at the first rectangle. When I is equal to 2, we're at the second rectangle. Okay, so if this was the right endpoint method, we just put xi. Because when I is equal to 1, we just want x1. That's the right endpoint. When I is equal to 2, we just want x2. That's the right endpoint for the second rectangle. But we can't do that here. For when I is equal to 1, what do we want? We want what's halfway between x0 and x1. We want x sub I minus 1 plus x sub I over 2. And then delta x. That's what we want. You see, it's more complicated, though. Okay, so with that, if we look here, so I is equal to 1. What do we want here? We want x sub 0 plus x sub 1 divided by 2. That's 2/5 divided by 2. That's 1/5. Okay, when I is equal to 2, we want x sub 1 plus x sub 2 divided by 2. That's 4/5 plus 2/5, 6/5 divided by 2 is 3/5. When I is equal to 3, x sub 2 plus x sub 3 divided by 2, that's 10/5, which is 2 divided by 2 is 1. Okay, I is equal to 4, x sub 3 plus x sub 4 divided by 2. So 6/5 plus 8/5 is 14/5 divided by 2 is 7/5. And then I is equal to 5, is x sub 4 plus x sub 5 divided by 2. That's 8/5 plus 10/5 is 18/5, so 9/5. Okay, so there we go. And to make this easier, let's plug this formula into our calculator. So x divided by x plus 1, x plus 1. Okay, we want to store this as e. Okay, so now we want to evaluate e with x is equal to, and we'll start with 1/5. Okay, that's 1/6. Okay, that's 1/6. All right, now we want to do the same thing with x is equal to 3/5. It's 3/8. Now with x is equal to 1, we can just, that's easy, so that's 1/2. Okay, now with 7/5, so 7/12, and then 9/5. Nine 14ths. Okay, so M5 is equal to 2/5, and then we've got, so 1/6 plus 3/8 plus 1/2 plus 7/12 plus 9/14. Okay, now, so 127 over 56, and then times 2/5. 127 over 140. Which is 0.9071. That's 4 decimal places. So there we go. Just like that. All right, express the limit as a definite integral on the given interval. Okay, so how do we express this as a definite integral on this interval? Well, all right, the definite integral is like this. We know from there's the limits of integration. We put some function and then dx. Okay, so to answer this question, we need to determine what is b and what is a. And that's easy. That's going to be, b is going to be 7 and a is going to be 2. But what's a little more challenging is, what do we put for f of x? Dx is easy. We just put dx, you just put whatever the independent variable is. But what are we going to put as f of x here? That's the challenge. So, all right, so this is going to go from, the limits of integration are 7 to 2. But what is f of x going to be? Well, we see we've got these xi stars. Like here's this is delta x. This is like the dx. Okay, like this is the width of the rectangles. They're all the same. You can factor this out of the sum, and so we're just really looking at, here's the height of the rectangles, and we know that the height of the rectangles, that's associated with, you're evaluating the function at some point within the rectangle. That's what the height of the rectangle is, and that's where the function comes into play. Okay, so what point are they evaluating the function? So within each interval for each rectangle, what point are they evaluating the function at to get the height of the rectangle? Well, what this xi star means is that you can pick any point you want. You could do, for the first interval, you could do the left endpoint. For the second interval, you could do the right endpoint. For the third interval, you could do the midpoint, or you could do all left point, all right endpoint. It doesn't matter. And these xi, this xi star is used for, like, yeah, if you were doing an approximation, if you were like doing from I is equal to 1 to n, to n is equal to 100, then this is kind of ambiguous, because it just depends on whatever you want. You can choose whatever you want. Someone could choose, you're not going to get the same answer every time if you're doing this from I is equal to 1 to 100. because it depends on whatever you choose for each rectangle. You could do the left endpoint method, the right endpoint method, the midpoint method, or some mixture. But what this is used for, this notation, the main point of this is because when you take the limit as n goes to infinity, then it doesn't matter what you choose. You're going to get the same answer no matter what. If you use the left endpoint, the right endpoint, some mixture. And so that's why this xi star is used for like the definition of the integral, is to help indicate that all of the different methods converge to the same value regardless. And so what you can see then, what that's showing us is that they're just saying you're taking xi star, which is whatever point you want, and they're plugging that into the function. So this is f of xi star. They just plugged xi star into the function. They're saying for each rectangle, for I is equal to whatever the number is, evaluate the function at any point you want within the interval. So with that, we can see what the function is. The function, we just read it off here. It's 5x cubed minus 4x. That's the function. So 5x cubed minus 4x dx. And we can write it this way because we have the limit as n goes to infinity. So that's why these two are equal. This here is equal to this. If the limit as n approaches infinity wasn't there, then it wouldn't be equal. This would be a Riemann sum. But since you're taking the limit as n goes to infinity, these two are equal. The graph of G consists of two straight lines in a semicircle. Use it to evaluate each integral. So what this problem is trying to do is it's illustrating how these definite integrals are literally just areas under curves in this sense, right? There's other applications where you can use a definite integral outside of just areas under curves, but for the way that we developed the meaning of the definite integral in section 5.1, we did it using areas under curves. And so what they're saying is that, like, this is the area of a triangle, this is the area of a triangle, this is the area of a circle, or a portion of a circle. So we can evaluate this using geometry. We don't need to use the Riemann sum here, which is just an interesting perspective on definite integrals. And so what is this integral here? This is g of x from 2 to 0. So that would be, 1, 2, or from 0 to 2. Well, it's just the area of this triangle, literally. 1/2 base times height. 1/2 base, which is 2, times height, 4. Okay, this is 4. 1/2 times 2 times 4 is 4. Okay, what about from 2 to 6? From 2 to 6. That's just the area of this semicircle, but since it's in the negative below, it's in the negative region, it's below the x-axis, it's going to be a negative. The area of this semicircle, but negative. So this is a circle of radius 2. So pi r squared, so 4 pi, but divided by 2, because it's half a circle, so 2 pi, but negative. Negative 2 pi. That's it. All right, from 0 to 7. 0 to 7. This is going to be the net area. So we're going to do, this area is positive 4 from 0 to 2. Then we're going to subtract 2 pi, and then we're going to add the area of this triangle. Base is 1 times height 1 divided by 2. So add 1/2. 4 plus 1/2, so 4.5 is 9/2. So 9/2 minus 2 pi. Evaluate the integral by interpreting it in terms of areas. So how do we evaluate this integral? Well, you can look at this. So, you know, if you've already taken calculus, or you're familiar with the fundamental theorem of calculus, you know, it's nice to be able to say, well, let's take this antiderivative. But we can't do that. We haven't learned how to do that yet. But based on the properties of definite integrals, we do know that we can separate this up into two definite integrals. So this is equal to, we can do this, 1 dx, and then we can do that. Okay, now we talked about how to interpret this. This is the function, this is the definite integral of the function f of x is equal to 1. So the function is constant over the interval from -3 to 0. It's positive 1. So what's the area under this curve? This is 1, 2, 3, 1. This is a rectangle from -3 to 0. This definite integral is the area under this curve here. What's that area? It's positive 3. You might say, well, what about the -3? Are we multiplying -3 times 1? No, we're going from -3 to 0. -3, 0 minus -3 is positive 3. If we flip this to have the upper limit be -3 and the lower limit be 0, then you would be multiplying it by -3, the height. But we're going from -3 to 0, that's positive. You go from -3 to 0, that's positive 3. Height is positive 1, so this definite integral is 3. Okay? Well, what about this? Well, this is we have a circle here. That's the key. So the equation for a circle is x squared plus y squared is equal to r squared. And that would be, so we would do, so like that. So the radius is root square root of 9, which is 3. Yes, the radius is 3. And then, so y squared is equal to 9 minus x squared. Take the square root of both sides, but we would put plus or minus, but we're not. And the reason for that is, so we can interpret that as, all right, you got the circle here, centered at the origin, radius 3. Okay, okay. So, like that. I didn't draw it. It's not the best. Something like that, okay? It should be radius 3. Okay, so when you solve for y, this would typically be plus or minus. And so the idea is, if you plug in x is equal to 2, that's the square root of 5. And so that, I don't know where exactly you're at, like around here. But it's plus or minus, right? It's here and here. But when we take off the plus or minus, then what they're saying is we're just looking at the positive side. If you put a minus on it and not a plus, you'd just be looking at the negative side. So that's what this is. It's the half circle above the x-axis. And so what they're doing is we're looking for this area here from 0 to 3. It should be, we're looking for this area. So it's a quarter of the circle. And so what you do is, we know that then in that case, we're going from, well, no, I'm sorry, it would be from -3 to 0, it'd be this. Okay, but so that's pi r squared, 9 pi divided by 4. It's going to be positive, right? -3 to 0, it's positive. You're going, that's positive 3. And then this, we're looking at, they're not saying minus here. It's above the x-axis. So this is 3 plus 9 pi over 4. There you go. That's what this is.